Look off to the side, by the way. When I look off to the side, it's I have two monitors, so the chat is on one screen and then my camera is in the front. So just wanted to also put that out there. But again, thank you. So let's talk about firstly, before we even get into Edge Impulse, what exactly is EdgeML? So EdgeML, also called various other things like TinyML or embedded machine learning, was actually inspired at Google by the keyword "Okay Google" for virtual voice assistants on your phone. So a algorithm for on-device machine learning was created specifically so people could do things like Hey Siri and Hey Google. And the focus here was, how can we create a really small machine learning model to detect voice events and audio events like this on our phone without taking up too much memory? Because our phones are used for a wide variety of things already, like web browser, games, actually being used as a mobile telephone, and various other operations. So we want to make sure that the operation or the software that is being run on the device to detect this event is really, really small and really efficient. So basically, Google generated this thing called TensorFlow. And the focus on TensorFlow was to do inferencing on the device rather than training of the machine learning model on the device. Because if we have to retrain the machine learning model on the device every single time we want to detect a keyword, that's going to take up too much processing and too much time. And if you don't know what a machine learning model is, it's basically just a mathematical function with a lot of different parameters. And these parameters are what we deploy onto the device to determine these events. So we'll talk about that more in the workshop of how we actually train these machine learning models and what does it mean to be deploying our machine learning model onto the edge rather than hosting it in the cloud. But the main things that the tiny machine learning and embedded machine learning industry focus on is maintaining high accuracy, basically saying, I want to be able to hear this OK Google term 100% of the time, while also focusing on speed, but not compromising on other various things like optimization of memory on the device. And this is specifically targeting battery-powered microcontrollers, but we can also look at things like on our phones, on Linux devices, and even on larger computers as well. Because all of these optimizations that we've done in TinyML also apply to all of these larger computers as well. It just is even more fast than it would be on a tiny computer like a microcontroller. And like I said, machine learning on the edge is primarily focused on machine learning algorithm inferencing directly on the device, rather than sending the raw data that we collect from the sensors on our device, i.e. the microphone on our phone, rather than sending all of that raw microphone data over the internet to the cloud and doing the processing of our machine learning algorithm there, we're doing the processing of our raw data and the result of our machine learning inferencing directly on the device. And we do this primarily with signal processing and trained neural network parameter. And this is very, very useful for any use case that has messy, high frequency data like audio applications. So how does Edge Impulse come in here? We've seen that TinyML is actually really useful. We know we can do many, many things with machine learning models, but I don't necessarily know how to write machine learning code. I don't know how to train a model. How do we even get my data off of my device? Well, this is where Edge Impulse comes in. So Edge Impulse allows you to completely, from end to end, develop edge machine learning applications, all the way from collecting and building your data set with your training and testing data for your machine learning model, designing and developing and training these machine learning models, and also includes extracting the most important features of your data with digital signal processing. You can also accurately test your model directly in the Edge Impulse platform, and then finally deploy. And the deployment that you can get is included in the Edge Impulse platform includes all of the code that you need in order to deploy it onto your edge device. So there's no black boxes. Everything is built for you, and is a very simple process in order to integrate it into your application. And in some applications, like today in our workshop, we won't need to write any code at all, and it'll just be a matter of selecting a few buttons to deploy the model onto our mobile phone, so we can do some keyword spotting directly on the edge. So this is the flow that the Edge Impulse platform completely handles for you, all the way from collecting your data to deploying onto your device. And I know some of this might not make sense right now, but it will definitely make more sense as we go through the platform later, so just bear with me. So the Edge Impulse Studio is actually used by 40,000 developers. We have over 75,000 projects created in the platform, and we have over 1,000 enterprises registered as well. We're also trusted by leading enterprises and in many of our spaces in the embedded industry, such as the Oura Ring, which produces fitness wearables, Advantech, Polycom, that has various wireless headsets and a meeting hardware, NASA, and Sony. We also handle any sensor, any data, and almost any use case. This is just a little chart that shows you the various types of microcontrollers or computers and what various use cases these can handle. So today we're going to be focusing on low-end and high-end microcontrollers, specifically for audio classification. But at the top here, where you can see anomaly detection, sensor fusion, audio classification, these are the various things that as you increase the complexity of your sensor data, the more computer processing power you'll need to run your model. But as we get more and more advanced in this space, we'll see the memory requirements needed for these types of use cases dramatically decrease. So even just from a year ago, this chart has completely changed. We did not used to have video classification. Object detection was not necessarily possible on an MCU. And here we are in today's age. So now that we've discussed Edge Impulse and we've talked a little bit about what Edge ML is, how does this relate to consumer audio applications? Well, I just have a little list here of various use cases. I'm sure people who are attending this webinar are familiar with various audio applications for things like wake word detection, like I mentioned with OK Google and Hey Siri. We can also do things with head tilt volume control and acoustic event detection. We can do keyword detection for device control. You can also use your voice to control modern user interfaces, like for people with disabilities on your mobile phone. You can do real-time transcription, ambient noise identification, and also background noise canceling as well. And also speech synthesis and speaker identification authentication, and more. Today, we'll be primarily focusing on wake word detection, keyword spotting, keyword detection, and acoustic audio event detection. And these things are all things that can be easily done within the Edge Impulse platform. And so along with wake word detection and keyword detection, these are both use cases that apply directly to hearables. So modern hearables are primarily doing a few things. They're rendering the received audio in the wearer's ear. They're capturing the spoken audio from the wearer's mouth. They're calculating anti-noise and rendering it in the user's ear. And these existing hearables or these existing headsets usually only use DSP or digital signal processing techniques to accomplish this goal. That's great, and DSP has been around for a long time, but these are usually very highly specialized algorithms, specifically for the one use case that the hearable is going to be using it for. So how can we use Edge ML combined with DSP techniques to further increase the usability of these algorithms on various other devices, and also reduce the time that you need to take in order to develop these models? So DSP-only workloads, as we can see on the left, they're quite messy. They're still really good for various devices, and DSP-only workloads usually take a small memory footprint. And in the past, if we wanted to also do ML, that would take a dramatically more memory on the device, which for hearables and headsets, they have usually low computer processing power and memory. So that's not going to be very good. But as we've developed TinyML and developed in this industry, now we can do both DSP and machine learning techniques, completely transforming every use case like wake word detection and making the model even clearer and even more accurate. So we've seen that keyword spotting it can be accomplished very easily and very efficiently and accurately with EdgeML and DSP processes. But what exactly is keyword spotting? What is it actually doing? How do we accomplish it? And we'll also talk about few-shot keyword spotting, which is a brand new technique that Edge Impulse has been innovating on within the last year or so and is available in our platform. So how does keyword spotting work? Well, keyword spotting basically works by collecting our data. In this case, we're looking at a signal for yes, when the user says yes or no into the microphone. We'll collect a bunch of these samples and upload them into the platform. In order to do our digital signal processing techniques, we'll use a feature extraction tool called MFCC, or MEL frequency central parameters. We'll talk about that more in the full live studio workshop as well. But this is basically just taking the most important aspects of each audio signal and pulling them out in a numerical fashion in an array. And these are the parameters, or these are the numbers that we'll use to process and train on our neural network. So based on the most important features from our DSP, we'll then pass those into our neural network, which will then train to recognize, okay, of the numbers that I have from this array, what are the most important and what are most representative of the keyword yes? And I know this is kind of abstract, but again, you don't need to know how to write any of this code in order to write this neural network and train this neural network with the Edge Impulse Studio. So a typical keyword spotting model does a few things. Like I said, it extracts those features using the DSP MFCC algorithm and feeds them into the neural network. And this neural network is either considered a 1D or 2D convolutional network. Again, lots of terms, but basically all you need to know is it's basically taking all these numbers and finding the patterns in these numbers that we've extracted from our DSP algorithm. And this will dramatically reduce the amount of processing power and RAM and memory usage we'll need on the device, because we're no longer just having to use the raw data and the digital signal processing. We can now just take the results of the digital signal processing and pass those into our trained model. So we'll train a model based on the various DSP parameters and get an output from our trained network. And so that's how keyword spotting works. But now we have a new innovation in Edge Impulse called few-shot keyword spotting. So basically the problem and why we created few-shot keyword processing is basically that in order to create a keyword spotting model, you generally need a very big, very diverse data set with many different audio sources. So if I wanted to create a really, really highly accurate model, sure, the model is small in the end and it will fit on the device, but in order to make this model super, super accurate for all of my real world use cases, I need to have a really big, really diverse data set. I can give you an example. My coworkers created a yes/no keyword spotting model. They recorded their voice saying yes, no, and they've uploaded those samples into the Edge Impulse tool. But because all of my coworkers are men, all of the audio samples were actually a very low frequency tone. So when I wanted to use the keyword spotting model that they trained, my voice was not recognized. So these are things that you have to keep into consideration when you're creating your keyword spotting models. And so if you can imagine, these are all English speakers as well. Native English speakers. So when we created this model of men and native English speakers, of course, my voice was not recognized, but I can imagine people who are not native English speakers, when they say yes or no, their voice might not be recognized as well, because with their accents, the keywords yes or no might not be recognized because the model just wasn't trained on it. So this was a big problem that we wanted to solve in the Edge Impulse tool. We don't want to have everyone uploading, massive data sets to their project in order to create a simple yes or no keyword spotting model. So this is where few-shot keyword spotting came in. So in order to create this first model, this is without FuseShot, we uploaded 560 samples. About each sample of yes or no was about 1 second each. So 560 seconds of yes or no uploaded into the project. We also have 2 more classes, which I'll explain a little bit more about what machine learning classes are in the workshop as well. But we also have a noise class uploaded to help the model more accurately identify when yes and no are spoken compared to the background ambient noise and just people talking off in the background. And unknown. So unknown can be a class of samples of any other word that is not yes or no. So we uploaded 560 of these samples. We balanced them such that 80% of the samples were in the training set, 20% of the samples were in the test set. And then we use these samples in our DSP algorithm to extract those important features, sent those features into our neural network and train the model. And this was the resulting performance without FuseShot keyword spotting. So the accuracy of the model only turned out to be about 75% accurate because there wasn't very many samples. In the grand scheme of things, for basic keyword spotting, 560 samples for a yes or no model is not going to be enough to get a super, super accurate model. If you're just doing home automation, something hobbyist on your own, this accuracy is actually just fine. But for consumer audio applications, you need something a little bit more, at least closer to 100% than 75% accurate. So once we added 10 or 11,000 samples, we increased the accuracy of our keyword spotting model by about 12%. Which for 19 times the data from our first model to only get a 12% increase in accuracy, that's not very good. That's a lot of work for us, only a small amount of accuracy increase. So, 87% again is great for hobbyists, but not so great for a, consumer level professional headset. So what can we do to improve that even further? Well, the solution is to do a different type of neural network model to take our extracted features from our DSP algorithm and apply them to keyword spotting. So transfer learning is another application for neural network and machine learning training that we have done for images. But we're instead applying that same sort of neural network architecture that we use for images to identify when something is or is not in an image to audio. So in transfer learning, we're basically taking a huge data set of tons of different labeled images. So for example, we have an image here with a dog in it. And this image is labeled and sent through the neural network to identify whether there's a dog, a horse, a ship, a truck, etc. in the image. We can also use so basically, this is called an ImageNet, where there's thousands and thousands and thousands of labeled images sent into a neural network, which is trained, and that resulting model through a concept called transfer learning is called an ImageNet. And in order to apply this to new images or images that the model has not yet seen, we can upload a brand new data set of things like, for example, we have here lymphocytes, various different types of cells or diseases. We can upload those labeled images and train a new model based off of the original ImageNet to label and find those and to identify those new images that we have uploaded to our test set for cancer cells, for example. So if we can apply this transfer learning algorithm to images, our team decided, hey, can we apply the same sort of idea of transfer learning to audio applications? If I can say that I have a long stream of data and I know where yes or no is located in the stream of data, why can't I train my model to do few-shot keyword spotting using a very small amount of training samples to produce the same result as in transfer learning for images? So that's what this looks like. So we can have so basically we have, with Harvard, a huge data set of various different utterances of of languages in many different languages. We're doing the same concept that we did for ImageNet for transfer learning in the previous slide, but now we're doing it with audio. So then if we take this huge data set of various different languages and various different words that are labeled, we can train a model on that audio data. And that could be like basically we call it the audio net. We can then only upload just a few samples of our voice saying the term that we want our new keyword spotting model to identify. For example, I could upload me saying a few samples of "Hey Jenny." I could upload those to Edge Impulse, and then I could then take the audio net that we have from our Harvard set and apply that to the training that I'm using on my voice, "Hey Jenny," and I'll get an output of a model that is extremely accurate compared to the old way of doing keyword spotting, which is uploading of 10, 11,000, 12,000 samples. We can do the same thing in a dramatically decreased amount of sample size or sample data set. So just from uploading 20 occurrences of each keyword, in this case, we're looking at the keywords green light, okay edge, red light, etc. In this case, we just had a few people on our team upload 20-ish samples of their voice saying these keywords. So there's like maybe under 100 samples uploaded to this data set, just with the applications of few shot keyword spotting, or that sort of quote unquote audio net that I described to you. Of course, that's not the official name, but that's sort of how I want to describe it to you. Applying the principles of transfer learning to this audio data set, we have increased the accuracy of our keyword spotting model from 87% using 12,000 training samples to 97% accurate using only under 100 or 200 samples. And this will make a little bit more sense when I show you in the studio, but this is a dramatic increase in accuracy with a very small sample size. And this is using a variety of training samples from our team. And this model will be accurate on a wide, diverse set of people who are then going to be using the model. We could then use this model trained with the transfer learning neural network architecture on not just native English-speaking humans, but other people as well who don't necessarily have the same accent as the people that this model was trained for. So this is extremely good for consumer audio applications because you can quickly create a keyword spotting application for things like green light, red light, for users that are going to be using it all over the world, who have different accents, who have different pitches in their voice, who use different tones. So this is a great tool for that. And it's, again, available for us to use in Edge Impulse. And I just wanted to pause here and show a little demo of this, and then we can do it on our own as well. But my coworker, Luis, has created a Getting Started Wizard video that will go through, I don't know actually if there's audio. Let me see. Share computer sound. Okay. We're just going to watch this video of my coworker Luis doing a demo of this few shot keyword spotting, and then we'll go ahead and do it all together as a group, or you can just watch me do it. And let me know if you don't hear the sound.
We can hear
Hey
the sound.
everyone, this is Louis from Edge Impulse Developer Relation Team. In this video, I'm going to show you how to get started with Edge Impulse within 5 minutes. We are going to use the keyword spotting technique to recognize your own sentence such as OK Google, Alexa, Hey Siri, etc. To get started, go to studio.edgeimpulse.com/evaluate. You don't even need a login to get started with. And you just need to follow the flow. Let's build your first model in 5 minutes. Let's type your first words, hello Louis, and next collect some data. I'm going to record myself saying hello Louis for 38 seconds. Let's do that. Hello Louis. Hello, 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 Louis. This is it. Now the model will check if we have enough sample data, which sounds to be the case. Next, I'm going to add some other data. So it's going to mix some other keywords and some background noise. Just click on the button and then it will do that automatically for you. In the end, you will have a proper data set that will be used to extract some meaningful information using some digital signal processing techniques. Here we are using the MFE. So I can click on next, and then you can change after the parameters here if you're interested in changing that. And if you're familiar with digital signal processing, note that we have several other blocks that can be used in the future. I'm going to generate the features. And one of the good things after that, it's the possibility to see in the Feature Explorer if the data are clustered in some different parts. Hopefully, this is going to be the case. Let's wait for a few more seconds. It is finishing up, and now we can have an overview of the Feature Explorer of where our data are clustered. I'm going to continue with the wizard, and then we are going to train our neural network. It's getting trained. I will just need to wait for a few more seconds again. So here on the right panel, you can see the output of the neural network being trained. We are approaching an accuracy of 0.9697. Once our model is fully trained, then we are performing some calculation based on the quantized and the unoptimized model just to measure the on-device performances, and you will have the outputs in a few seconds. Okay, now the model is trained and we can see the inference time here below the wizard. We can see the on-device performances. I'm pretty sure it will show up again later, but we can always go back to this page after. Now, if I want to try my model in real time, just follow the flow, and then we'll be able to see if it works. Okay, so now I'm going to speak, so the words are unknown. If I don't speak at all, it's some noise. And then if I say, hey, Louis, hey, Louis, hey, Louis, hey, Louis. Okay, so we can see that it's getting recognized at some point. Note that you can go back to your project and add some more data to build a more robust model. Thank you for watching.
Great. So that was sort of just a short video, very quickly explaining what the few-shot keyword spotting is doing. And sorry, I'm gonna pause this. And we use this specifically to show users how quickly you can get started with the Edge Impulse Studio tool. And we can all get started if we wanted to right now. I don't want to do that. Before I talk about validating real world performance, if people are interested, we could go through and do this all together. But basically, you don't even need to create an account for this, I don't think. But if you go to studio.edgeimpulse.com/evaluate, and I'll paste this link in the chat. This is how you'll essentially encourage users to upload to your project. We will also all create a crowdsourced keyword spotting model that includes utterances of various keywords to a group project. And there's a very easy way that you can send a link to your users to upload keywords to a project that you created in Edge Impulse. And I have instructions for this on a workshop page that I'll also send in a moment. But someone asked a question about that in the chat. And so that's basically how you can encourage people to do that. And all of these Crowdsourced keyword spotting tools are freely available in Edge Impulse as well. So for example, if you wanted to create a keyword spotting model that recognizes a few, French keywords, Dutch keywords, Danish keywords, and you can't really find a keyword spotting model that already does that, you can easily create one in the Edge Impulse tool, have all of your colleagues, have all your friends upload their voice saying your Danish, Dutch, French keyword into the Edge Impulse Studio, train a model, and then you have a brand new, really highly accurate keyword spotting model that identifies this brand new word. So we can just very quickly follow the same thing that we just watched Louis build. Today, I want to do the keyword, let's do Danish sound. That will be our keyword for this little example. We're going to collect our data. So I'm going to record myself saying Danish sound, click allow. Danish sound, 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 Danish sound. And looks like it only got a few of them. It might be because my microphone is working overtime, but what essentially happens is this same tool that you use to upload the samples of your own voice, it's basically doing various signal processing techniques to take the long recording that you have of all of your Danish sound samples and snipping them up into each 1 second samples. So that same tool that we use right here is the tool that you'll be able to send your colleagues to get recordings of their voice. Danish sound. So we can either upload some more, or we can just, let's just upload a few more here. I think I might need to do it on my phone. Try again. Danish sound, 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 Danish sound. I think it's because my microphone is working overtime, but essentially you need around 13 of these samples in order to start making your keyword spotting model. But we already saw Luis do that in the video. But if you're following along with me right now, feel free to put it in the chat that you're doing this process. If you go to studio.edgeimpulse.com/evaluate, and I'm happy to wait for you, or we can all do it at once. I know it's a little difficult because I'm also doing this webinar and you're listening to me and you can't record yourself. But great, I'm sure it's working for y'all. I'm pretty sure my microphone is just working overtime right now, so it's not doing the signal processing correctly. But we can look at a different project that I already have uploaded as well. So this is what your, obviously you will not have 27 minutes of data uploaded, but this is what the data acquisition page will look like for you after you followed the wizard. Yeah, my microphone's working overtime. I'm also not sure which source it's using for the microphone. Isn't that how it always goes, live demos, you know?
Yes.
But I also showed you the video, so I'll post that video in the chat as well for people who want to follow along. But the Getting Started Wizard is actually really easy as well. So let me know how that goes. So here's the link to that video that I showed you with Luis. So moving on, we'll talk more about what this video showed in terms of the neural network training, the DSP feature extraction, the feature explorer, all of these things that we learned in this video, we'll talk about very soon as well. So now that we have done a very quick keyword spotting model using the few shot algorithm, let's talk a little bit about how this actually affects real life performance and how do we actually validate that within the Edge Impulse Studio. So we saw the 88%, the 97% accuracy. This sounds amazing, but what does it actually really mean in terms of real life audio applications, real life consumer professional level headsets? Is it actually 97%? Is it actually 88% accurate in real life? Well, this model testing results tab really only shows us a mathematical percentage of how many of our test samples that were uploaded are correctly identified or correctly predicted to be the expected label that we put on the sample. So for example, of the 100% of our Hello World or our Danish Sound samples, OK Google samples that we uploaded to our test set, of the 100% of our test samples, what percentage of those samples were actually correctly predicted to be Hello World after we trained and outputted our model? And so these are samples that the model has not seen before. So that's just basically what this table is showing us. And for these test samples that were recorded in a very controlled environment like this office or at your home, they're not very indicative of what real world sound will actually be like in the real world. When I say hello world on a subway or in a metro, that's going to be a much different recording than me saying hello world in this controlled, quiet environment. So this 88%, it means it's 88% accurate, but it only means it's 88% accurate based on the test set. So how do we actually validate it for real world results? Well, we actually have a brand new feature that's going to be coming out in the next few months called the Application Testing tab. And the Application Testing tab is going to be taking your testing samples and augmenting these test samples, these 1-second samples that you've uploaded in the controlled environment, augmenting these samples onto 24 hours of real world ambient data. And this could be just a metro recording, a very busy office recording, and they're going to take those test samples and put them into this 24-hour length, very long audio data set. And then it's going to process the 24 hours of real world audio data with your augmented test samples onto it to determine how many of those test samples that you augmented onto the 24 hours of real world data were correctly and incorrectly predicted to be the keyword was found. I'm not sure if it's making total sense, but the metrics that we use to identify how accurate your model is on real world data are these two terms, FAR and FRR. So FAR is in terms of, actually I have a note here. FAR is in terms of how many times your model was activated correctly based on it saying, hey, my keyword was found correctly, yes. And FRR is how many times my model rejected, like it felt that it found the keyword, but it actually, based on the results of the model percentage, in terms of the accuracy percentage, it was rejecting it. So how many times was it falsely activated? How many times was it correctly activated? How many times was it correctly rejected? How many times was it incorrectly rejected? These are much more detailed results that you can get to evaluate your real world performance. We can also use these FAR and FRR results to understand the impact of post-processing for our real world data. And the application tab, I can show you a little demo of this in a moment. But so you'll be able to record and hear the real world 24-hour data set sample with your augmented test samples onto it, and find exactly within the sample the start time and the end time when your keywords, yes or no in this case, were correctly identified, when the start time and the end time happened, and what is their reject and activation rate. And I'll show you that live in a moment, but it's really, really cool. And these are metrics that are used by companies like Sentient to evaluate the actual consumer level accuracy of their audio applications. So we have that supported directly in Edge Impulse with our partners Sentient as well. So this will be coming out with the application testing tab in just a few months. So this is also very useful. So now that we've sort of discussed what FAR and FAR and FRR are, we can use these various, basically, they're sort of ratios. We can use these ratios to say, hey, I want my model to be more leaning towards false activations. I'd rather have my model say, this is most likely yes, or I'm hearing most likely yes or no, than have it to be falsely rejecting. This is when it really depends on your use case. For example, for keyword spotting, just as like, hey Google or hey Siri, false activation and false rejection is not super important because your phone, you don't want it to activate all the time because that would decrease the battery life on your phone. But you want it to activate most of the time. So this sort of ratio of things isn't super important for low risk applications like hey Siri, hey Google, keyword activation. But if I have a model that is hearing various things like glass breaking, a person falling, I want my model to be very accurate and not falsely rejecting things that should have actually been identified as glass breaking, a person falling, etc. Because I want my model to be way more accurate on saying, hey, this is actually an event that needs to be identified. If I don't identify this event, a human could potentially be hurt, etc. So the trade-offs here between FAR and FRR are very important depending on your use case. Sometimes they don't matter at all. Sometimes they mean difference between getting to the hospital in time. So that's also going to be available in the application testing tab. So let's just take a look at that tab now that we've sort of talked about it. This Zoom thing is okay. So in this project, I basically have a yes or no keyword spotting, and I'll have all these samples uploaded again. About 55 minutes of data here because we have a bunch of people on our team uploading to this project. But soon, as I mentioned, this application testing tab is not yet available in the studio. So if you've created an account and you're like, where is it? It's not available yet. But after you have trained and upload all of your data and trained your model in the studio, you'll get access to this application testing tab that shows you everything that I just showed you in the Google Slides. So there's a bunch of information here. You can choose between various ratios between false activation rate and false rejection rate. The one that is chosen by default is the lowest combined FAR and FRR. So based on all of the test samples that we have uploaded to our testing tab, based on all the test samples that we have uploaded to our test data tab, and the ones that have been augmented onto our 24 hours of real world data, we can see how many of these yes or no keywords were identified to be true positives, true negatives, and false negatives. And the ratio of these true and false positives and true and false negatives is what determines our FAR and FRR. And you can rebalance these ratios to, again, determine for your use case what is most important to you. By default, we want a low overall FAR and low overall FRR. We can also hear what the 24 hours of real world data sounds like and when we have seen a false negative, for example, or a false positive, and hear what that sounds like. This is in beta, so I guess I am having a little bit of trouble here moving it along. But basically what you'll be able to do when this is live is you'll be able to click right here and hear what that sounds like. I'm going to tell you on about this. But you can see basically of the 24 hours of sample real world life data that you've uploaded, a lot of it is just noise because that's what your microphone is hearing all the time. Sometimes you'll hear people talking in the background, and then it's waiting for, the model is waiting for when it falsely or truly hears yes or no, and it outputs the model's inference prediction accuracy percentage on a scale of 0 to 1. The closer it is to 1, the higher percent of accuracy it is that the keyword was actually heard. So that's the application testing tab. That's going to be really awesome. We'll be releasing that sometime this year. And then finally, there's just another thing that I wanted to talk about before we get into the workshop again. We have another tool to make keyword spotting even better. There's a lot of various different types of neural network applications and neural network architecture layers that we can use to train our model. I'm not a machine learning engineer. I just use Edge Impulse. So when I'm talking about neural network architecture, I'm mostly just using what has been chosen as the default for the type of sensor data that you've uploaded in the tool. And that's how Edge Impulse works for all of our free users. If you upload a audio data, we will automatically recommend a neural network architecture for you based on the data that you've uploaded. So in this case, you'd choose an MFCC DSP block and the various neural network architecture layers that are best for audio data that have small sample length. 1 second. This will make more sense again when we go into the studio. But there's a ton of other type of neural network architecture layers and parameter options that you can choose for your data. And there's almost an unlimited amount. So you can combine layers in almost any different way to get various levels of accuracy output, memory usage, and more. So if we take our keyword spotting model where we input our yes or no samples, we extract those features using our DSP algorithm, MFCC, and pass those extracted features into our neural network, you'd think you'd get the same percentage accuracy every single time, but when you change those neural network architecture layers, you can get a very drastically different model output. And what we're looking at here is primarily for performance calibration. Depending on the device that you want to deploy your model to, you might want to put more resources into DSP, depending on the type of processing power and processing capabilities you have on your device. Or you might want to optimize for the lowest amount of memory, or you want your model to primarily have the most memory towards neural network. This will make more sense in the EON Tuner, which I'll show you in a second. But this is available for audio, motion, and vision applications. But basically, you just click the target that you want your model to deploy to. And all you have to do is click one button, Start EON Tuner. And this goes through thousands of different combinations of neural network architectures and DSP configurations to output a very long list of all the various different types of percentage accuracy models you can get in their various different input parameters and computer architecture layers, neural network architecture layers. And you can select that and replace that in your current Edge Impulse model or your project and use that to deploy instead of what you've previously selected as the default. So depending on what you want, if you want to choose more DSP, less NN, more memory usage, less memory usage, depending on the hardware, you can get a stronger model that uses a lot more memory. And you can basically reuse the data that you've uploaded for your project on a ton of different devices just from a click of a button. And I'll show you that now. So this is a application that we have done where we have uploaded a bunch of bird sounds of parakeets and things like that into our data acquisition tab. So we have uploaded for a rose-ringed parakeet and house sparrow and noise. So this is a model that is detecting when a parakeet or a sparrow has been heard in your backyard, for example. And we'll most likely be using this on a very small target device. So in this case, we've chosen a Cortex M4F. And this has a very small target, well, not super small, but pretty small target ROM and RAM. So this is what we're optimizing for. So we can see that we want our inferencing value to be less than 1,000 milliseconds. The time it takes to get from raw data to inference result is the time per inference in milliseconds. And we can see a very large output of various different configurations for our neural network architecture and their percentage accuracy. So you can see that if you look at the bottom, this is basically our neural network architectures down here. These are wildly different from model to model, and our accuracy can still remain the same. So it really just depends on what you're looking to optimize for your device. And this means that you can reuse the same data set for a bunch of different types of devices, a bunch of different use cases, just from the click of a button. And this is also currently available today in the Edge Impulse Studio. So everyone can go ahead and start using the EON Tuner for any keyword spotting application, any audio application. In this case, it's not even looking at human audio, it's looking at animals. You can also do it for sensor data and image data as well. So that's the end of my slides. And I guess we'll now go into the workshop, which is basically just going through the Edge Impulse Studio end to end. I guess I'll stop here now. If anyone has any questions, please feel free to put them in the chat.
Thanks for that, Jenny. There was a question from Wiebke. Did you answer that already? It was a while ago.
I think I sort of did, but I will re-answer it again. There is a page that I'm going to send out. So this is the first workshop page, but on the second workshop page today, there's basically a tool that we have. So the question is, for few-shot keyword spotting, do you need each user to submit around 20 speech utterances for every keyword? Practically, how do you encourage users to do that? Well, for just you, if you're just uploading utterances of your own voice, we have the studio.edgeimpulse.com/evaluate tool. And that will automatically help you collect your own voice, around 20 utterances for each keyword, and upload them to your project. But in order to get others to upload their voice to your project, we also have this tool called the Keyword Collector that you can use to send a QR code basically to all of your peers. They can scan that QR code on their phone and upload recordings of their voice on their phone. And those recordings will directly upload to your Edge Impulse project. And we'll go through that as a group as well. I'm not sure how many people are on the Zoom, but we could all do that together as well. So yeah, so that's the answer to that question. We also have, I think we have a blog post about this that I'll link to.
And we have one more question here. Could you tell me more about the model and data versioning, testing, and deploying, or in general, MLOps approach or tools that you're using?
Can you repeat the question?
Yeah, it's in the Q&A as well. This is from Chungwoo. He's a professor at Aalborg University here in Copenhagen. Could you tell me more about the model and data versioning, testing, and deploying, or in general, MLOps approach or tools that you're using?
Yeah, so let me just really quickly post this link into the chat. there's a whole blog post about how you can do crowdsourced data collection as well that I created a few months ago. So I recommend checking that out. In terms of MLOps approach and the tools that we're using, let me put this on the product page. Edge Impulse uses TensorFlow as TensorFlow and Keras as the background for training your model. We also have a bunch of Python code that is used to do the DSP feature extraction, and all of that Python code is freely available and hosted on our GitHub repo. So I recommend checking that out. Model and data versioning, we have that built into the Edge Impulse Studio. We have project versioning, which basically takes your entire project, your various model configuration, the data set that you have uploaded at this current point in time, basically zips all of that up to its zip file, and you can restore to that project version at any point in time in the future from this tab. If you want to do various model versioning itself, we also have versioning itself for each neural network architecture that you create. So say I really like how this neural network architecture is performing for this Hello World keyword spotting model, but I want to do some fiddling around in it. I can also create a new version of this neural network architecture layer configuration itself directly within the project. And these various versions of my neural network classifier will also be saved in the project versioning tab itself. And again, like I said, everything in the Edge Impulse is not black box. So it looks like, it's a low code, no code, but all the code is available for you to view and see. And you'll get an output library that contains all the code you need with all the DSP configuration, all the neural network configuration, all the TensorFlow code. All of that will be available in a completely third-party dependency-free C library or any other type of library that you'd like to deploy to, which I will talk about in a moment. And I hope that answers your question. Please feel free to use the chat or the Q&A to ask more. But this long story short is TensorFlow Keras. We have versioning within the tool, and nothing is black box. You get all the access to all the code. You can also change the code directly within the Edge Impulse Studio via the expert mode tab, if you know how to write TensorFlow code. So yeah, so I just wanted to start and just go off from the top to the bottom, doing basically a tour of the Edge Impulse Studio and the various things you can do with it. Feel free to ask questions along the way, and then we'll go through and create a crowdsourced model.
That sounds good. Would you like to take a quick break or anything? Or are you happy just to continue?
Oh yeah, I guess we can take a break. Yeah, maybe just a few minutes.
Yeah, let's meet back in a couple of minutes.
Great.
Or do you want 5? Is 5 good?
What time?
I mean in 5 minutes.
Yeah, sounds good.
All right, see you then.
Thanks. guess I'll just get started in a minute or two. Once everyone's back from the, oh, did not mean to go to my email. Let me just close that. Thankfully, it was just on the email of Shelly. So I'm just making a public version of the couple, let's see, actually, this is the wrong one. Just making a public version of the Hello World keyword spotting model that I'm going to be going through now. I know we've talked, I think, hopefully you guys can hear me. We talked a lot about neural network architectures. We talked a lot about DSP algorithms and how that is related to audio applications on various edge devices. And that's it's a lot of terminology. It's a lot of, buzzwords. And now we're going to go through, we're going to drill down, deep dive into the Edge Impulse Studio and really see what this means, what this looks like in regards to our data. How do we actually do it? And how to use this tool. Because it's really quite easy, but because there's a lot of terms, this can be quite confusing, especially if you're brand new to the world of tiny machine learning. Looks like Ayush has a question in the Q&A. Is there an easy way to collect data from the device like Arduino or RP2040 without terminal? And yes, there is. I'm going to talk a little bit about data acquisition. Hopefully that finishes that. But I'm going to talk a little bit about data acquisition in a moment. But we have a bunch of documentation specifically for things like Raspberry Pis and Arduino boards and how you can directly take data from these devices and upload them into your Edge Impulse project. Specifically for the RP2040, I'll paste that link in the chat here. And I'll also send it to the Q&A. But this documentation page will go through step by step on how you can install the Edge Impulse tools that you'll need in order to deploy a firmware to your device like the RP2040 and start collecting data directly from this device and uploading them into your project. You will need to know some terminal commands, but it's directly through serial connection, and you might even be able to do the serial connection option with the daemon as well, depending on your board. I don't have one plugged in right now, but if you have any issues with that, please go to the forum at forum.edgeimpulse.com or email us at hello@edgeimpulse.com. Here's our forum. Okay, great. And I'm going to just put, oh, it looks like it's not completely done yet. Okay. While this is finishing up, I'm just going to go to the dashboard. So basically what I'm doing right now, before we do the deep down into the studio, it looks like there's a Danish question in the chat. Before we do the deep dive into the studio, what I'm doing right now is I'm basically versioning today's workshop's Hello World classifier, and I'm going to send that as a link that you guys can use to clone this project into your own Edge Impulse account. So the link I just sent, when it's ready, for now, you'll see this error. You'll see this error that says project has no public versions. Just wait a few more minutes while it's finishing up for storing those files and back uploading them into the cloud, and then you'll be able to clone. You should be able to clone the project to your own Edge Impulse account now. And basically, this is a read-only copy of the project that I'm going to be talking about right now. So yeah. Okay. So please feel free to ask questions as I go through this. This is going to be a lot of information, but like I said, we're going to discuss the fine details of how all of these buzzwords and how all of these terms about embedded machine learning are related to consumer audio applications like keyword spotting. So this is the dashboard of the Edge Impulse Studio. This is the page that you'll see after you clone the project of the link that I've posted in the chat. And this is also the page that you'll see when you create a brand new project and various other things. This is also the page that you'll see if you do studio.edgeimpulse.com/evaluate. So today I've created a project for a basic Hello World keyword spotting model. This model is not using the few shot keyword spotting algorithm. So this model is not as accurate for many different languages as the few shot keyword spotting models are, but it is still very accurate for our use case today, which is just a demonstration of keyword spotting itself in the studio. So this is the dashboard. Every project is basically equivalent to one machine learning use case. Today we're doing Hello World keyword spotting, but you'll also have a new project for other types of sensor data that you want to do, other use cases that will each sort of equivalent to one project each. You can see how much data you've uploaded here on the right in the summary. You can share your project. So basically what I did is I have allowed you to clone my project, and that's what we mean by sharing. You can add collaborators to your project here. And you can also download all of the intermediate block output for your model. So like I said, nothing in Edge Impulse is a black box. You have access to all of the same model information, NPY files, TensorFlow files that you would get if you trained your model using TensorFlow code on its own. So all that is available for you to download here. You can also export all the data that you've uploaded to your project from this tab as well, export data. So this is the dashboard. Now we're going to move on to the devices tab. So today I have very simply connected my phone to my project to upload new data. And we can go ahead and go through that again right now. If you scan this QR code that I'm about to show, you'll also connect your own phone to my project as well, which is essentially what we'll be doing for the Crowdsourced project in a little while. So I'm just going to go to the devices tab and click connect a new device. We have a almost limitless amount of options here for you to collect and upload new data. You can upload data from almost any source, almost any sensor. Of course, today we're going to be focusing on microphone data, but you can also upload data from accelerometers, temperature sensors, humidity sensors, cameras, images, video, all of that can be uploaded here. And today, because there's a microphone on my phone, I can very simply connect my phone to my project via my phone's web browser to collect new audio data and new keyword spotting samples. I can also upload data directly from my computer. I can use a fully supported dev board like I posted in the chat for the RP2040 and upload data that way. So I'm just going to show the QR code next to connect to your mobile phone. I'm going to take my phone out, scan the QR code on my phone's camera, and now my device is connected. And then actually, yeah. So then I'm just going to click get started, and I will be taken to the data acquisition tab. So I already have a bunch of samples here of my colleagues saying hello world. I'm just going to add a few more samples to show how easy it is to upload data directly from my phone into the project. So on my phone, I'm going to click all of these instructions are also available in the workshop page that I just posted in the chat. So I'm just going to click on collecting audio. I'm going to give my computer access, I'm going to give my phone access to my microphone. I'm going to set the label as hello world. And then I'm going to click start recording. Hello world. And I think this almost got hello.
Hello world.
There we go. So I've just uploaded a brand new sample very quickly, very easily, directly to my Edge Impulse project. And this process of basically sending that QR code is how you'll essentially do it for collecting recordings of your colleagues. So it's super, super simple. You don't need any hardware other than your phone to make a really highly accurate model. I can also connect using WebUSB, various other serial devices like the RP2040 or other Arduino boards, or any other embedded device that we have supported which you can find in the development board section of our documentation. And these boards are great for also doing prototype development for various other headsets, for example, which we have done with companies like Polycom as well. So back to the project, where to go? Okay. So basically just repeat this process for, in this case, since we're doing classical keyword spotting, we're going to need quite a lot of data. So we have about 27 minutes of data collected here. But if you're doing few shot, you only need a matter of a few seconds, maybe a few minutes of data in order to get a really highly accurate model. So we'll repeat this process, uploading data for both our training and our test data set. You can see our training data set here and our test data set here. And we'll need about an 80-20% split between our training and testing data set. This just makes sure that we can get the most highly accurate model that we can for the real life use case. And like I said, this performance that will be shown on the neural network training page is not necessarily indicative of real life performance, but we'll soon be releasing that application testing tab that will prove real life real life model performance on real world data. But this is the best we can do in terms of today's Edge Impulse Studio, which is the training performance. Okay, so before we get to that though, how do we actually design and train a machine learning model? How do we integrate the DSP algorithm based on the data that we have uploaded into the tool? Well, this is what we call impulse design. So this is basically the graphical version of the complete MLOps pipeline, from gathering and labeling our raw time series data or our audio data on the left, to extracting the most important features with digital signal processing, the white box here, we're using an MFCC box, taking those extracted features and inputting them into our neural network and training based on the configuration of the different architecture layers that we have, and outputting the different features that we want to identify from our data, in this case, hello world, noise, or unknown. And then the green again is our output features. And all of this is available for you to use with an Edge Impulse for free. This is the graphical format, like I said. But basically, these are just little blocks that are just little graphical blocks that are overlapping Python snippets, Python code snippets that have we created for you to use to extract the most important features from your audio data. We also have a bunch of other processing blocks available for you to use in the Edge Impulse tool for you as well for free. So we have MFCC, which is great for human voice audio like keyword spotting. We have MFE, which is great for non-human voice audio, which is what is likely used in the Sparrow and Parakeet model that we looked at a little bit earlier today. We have other types of processing blocks that are just Python snippets again in a web GUI platform. We have spectral analysis for accelerometer data, other sensor data, and we can also use raw data without doing any more signal pre-processing. There's an example that I did a while back with Doppler radar, and that Doppler radar chip was already doing quite a bit of processing on the chip. So I just wanted to make a model that was using the data on its own raw without doing any more processing. So that's a great way to do it in the Edge Impulse tool. So you can either use any of the pre-written blocks that we have here available for you, which again, the code for these is available in our GitHub repository, which I can also post right now. Processing blocks. So all of that code for our MFCC block or MFE block, everything that we'll be using today for keyword spotting is available in our GitHub repo. And so yeah, so you don't have to write any code to do this if you're using a pre-written block in the studio. But if you have your own processing block that you'd like to do, you're very familiar with audio signal processing and you have your own algorithm that you want to use, you can add your own custom block by following the instructions in our documentation here. It's really quite easy. You can use any language and you can just wrap it in a Docker container and add the link to your project. And then here we do our neural network classification. This is when we get the output features or output labels, hello world, noise, and unknown. based on the input features that we have from our DSP block. You can also add multiple other DSP blocks on top of each other and input the results of these DSP blocks into the same neural network classifier. So you can do some pretty fancy stuff in here without you having to write any code. But today, because we're just doing keyword spotting, we're going to take the output of our MFCC block and input it into our neural network classifier. And we have other learning blocks available for you to use as well. This page right here will change depending on the type of sensor data that you have uploaded. So here we can see regression, classification, and we also have our few shot keyword spotting transfer learning block available for you to use here as well. So we could also just add that right now and see what that looks like. And there's some caveats here. You need a certain type of resolution of audio data in order to use the few shot keyword spotting model. If you follow along with the instructions that I've pasted in the blog and other links that I have in this chat of this webinar, you won't have any problems. So we have our neural network classifier. This is just the classical keyword spotting, requires a ton of data in order to get a really high accurate model. We also have our few shot transfer learning model block as well. And these are just GUI blocks that are wrapping over Python scripts for TensorFlow. I'm going to click Save Impulse. And now we'll move on to our digital signal processing. So in order to train our neural network, we need to extract the most important features of our data. And extracting these features is important because we want to reduce the amount of complexity that our model needs for information to train on. If we just use the raw data of our audio, the resulting model from our trained neural network is going to be very large because it's going to need to have, it's going to recognize a lot of various complex mathematical parameters of our data, of our original data. And the model is just going to be very large because it has so much complex data that it needs to know to recognize those patterns. If we take out the key portions of our audio data based on various digital signal processing techniques, our resulting model doesn't need to be as big. And DSP functions today are very fast anyway, so there's no reason not to do DSP processing unless you have a DSP chip on the device that's doing it on its own. And that's another thing. So for this block, I've mostly left the parameters of the MFCC block the same or as default as what they would be chosen for you when you add this block in the Edge Impulse Studio. But if you know things about FFT lengths, filter numbers, frame lengths, frame strides, you can change all of those here. And again, these are simply just inputs to a Python function, which you can find in the GitHub repo that I posted here. So you can change those parameters here and save them. And this output over here, this DSP result for our conceptual coefficients and our process features will change depending on the sample that you have selected and depending on the parameters that you've inputted here. You can also see how fast this DSP algorithm will perform on the device. In this case, we are estimating for a Cortex M4F microcontroller. The processing time for this will take, to get from raw data to the DSP result of the process features here, will take 165 milliseconds and 17 kilobytes of RAM. So it's relatively quick for a relatively low power microcontroller. If we go to the dashboard and change the hardware that we are estimating our performance calculations for, this estimate will either increase or decrease. So if I change from a Cortex M4F to, for example, a MacBook Pro, we should expect that the latency calculations for the DSP block will be dramatically less. As you can see, the processing time to get from raw data to DSP results decreased from 165 milliseconds on the Cortex M4F board to 2 milliseconds on the MacBook Pro 16-inch. So we do all these estimates for all of the supported boards that we have and all the supported hardware in our system. So for example, you could even do the Arduino Nano, which is similar to the RP2040. Oh, RP2040 is actually Cortex M0 Plus. So that should be way different even from the Cortex M4F because the RP2040 has an M0 Plus processor on it which is a lower power device. So this process takes much more time. Let's change it back to the Cortex M4F. And this is just a general estimate. Okay, so we've determined our parameters. In this case, we're just going to leave them default because we're doing classical keyword spotting. And I'm not a digital signal processing engineer, so I'm just going to do what Edge Impulse says is most likely the best for my uploaded data. Then I'm going to move on to the Generate Features tab. The Generate Features tab, once I click on Generate Features, but I've already done that, extracts all of the most meaningful features from my data using the Python code that I've used for the MFCC block. And based on these extracted features, Edge Impulse does this pretty cool thing that outputs a 3D visualization feature explorer. And this feature explorer is really useful because you can very clearly and visually see how your three classes, hello world, noise, and unknown, look like before you even do any machine learning on them. So we already have really, really great separation here. You can very distinctly see the three clusters of hello world, noise, and unknown, which means that our model is going to perform fairly well without even having to do any machine learning. But once we do that machine learning, of course, the accuracy is also going to skyrocket. So depending on the type of sensor data that you've uploaded, and depending on the type of classes that you have uploaded and the quality of your data set, there's a lot of different factors here on whether you're going to get a good separation in your feature explorer. We have a really good separation today, but I've had some applications in Edge Impulse where this just looked like a cluster of sort of a meaningless cloud. That doesn't mean that your model is going to perform badly. It just means that your model will need a bit more time and a bit more information in order to train, in order to find those patterns in your data, in order to recognize when the audio is hello world versus when it's just noise, for example. You can also click on each individual sample and see where that where that sample came from and what it sounds like. So I could look in here and be like, oh, there's a green dot over here. I feel like it should have been hello world. We can hear what that sounds like.
Up.
So the digital signal processing sort of realized that this has sort of similar characteristics to hello world and noise. But again, this is why we need machine learning in order to help us really determine exactly what it's supposed to be. But digital signal processing already gets us halfway there. So moving on to the classical keyword spotting, this is our neural network classifier page. And it's very similar to the style of our previous pages. This is just a GUI version of a Python code snippet that we have available for you in Edge Impulse. And this, again, it's freely available. You can go and do it on your own right now. I've left most of these options here default, but if you know how to write TensorFlow code, you can click on these three buttons right here and switch into Keras or expert mode, and you can see exactly what these options in the GUI format look like in the Python code version. So it's really great. You can also write your own Python code here and do whatever you want and click start training. And it does the same output very similarly directly within your web browser, as you would with developing TensorFlow on your desktop. But we're going to switch back into simple mode here because I'm not going to write any code today. So we've set a number of training cycles, and this is how many times or epochs our neural network is going to train on, how many times we're going to pass through the data in order to recognize those patterns. We set our learning rate, our validation set size, and we also have other options available for you to use here for keyword spotting purposes, again, or other types of purposes to do data augmentation, which basically randomly transforms the data during training to allow you to get a even more accurate model without overfitting early. And this is, again, some more machine learning buzzwords, but it basically allows you to use your existing data in various other ways in order to get an even more accurate model. So we can add some noise bands, we can mask time bands, we can mask frequency bands in order to get a data set that's more indicative of what a real world data set would look like, which will be even better for your model in the real world. So we have some architecture presets available for you to click on here. You can either click on the 1D convolutional or the 2D convolutional, and this will set up all your layers according to the one that you've selected. Today, it looks like we're doing the 2D convolutional. So you can also, change your architecture settings here, your layer settings. You can add other settings as well and other layers, all within the GUI version of this tool. Or again, you can do it in the Python version by going into expert mode. And then in order to train my model, so I've taken my extracted features from the DSP code or the DSP algorithm. I've taken those extracted features, I'm passing them through my architecture layers, and all I have to do is click start training, and Edge Impulse takes care of the rest for me. You can see the training output here at the top. This will just take a couple minutes, but since we've already trained the model, we can see what our performance is on the bottom right here. So we can see that we have 95% accurate because we have uploaded 30 minutes of training data, which is pretty good for our use case. You can also see each individual sample, what test samples based on the trained model were predicted correctly and mispredicted to be their expected label. So this one was predicted to be hello world, but it was actually labeled as unknown. So we can take a look at that. So this is obviously not hello world, but the model thought it was hello world. In this case, if we want an even better model, we could either do few shot keyword spotting, or we could upload even more data to get our model even more accurate for the environment that we're going to be using it in. So this is a great way to very quickly tell how your model is going to perform before you even deploy it onto your real world edge device like your phone or your microcontroller, etc. So you can also scroll down to the bottom, and similarly to the DSP tab, you also get an on-device performance information. You have the amount of time that it'll take to get from DSP extracted features to predicted inference result, and that's that. So that's 36 milliseconds to get from the DSP extracted features, pass that through the trained model, and get your predicted output, 36 milliseconds. This model will take about 8.8K of RAM on your device and 32-ish K of flash. So it's a pretty small model for what we're doing today. And again, these values will increase or decrease based on the selected hardware that you are using for your use case. And this will also change depending on the types of architecture layers and other parameters that you've chosen for your model as well, which we'll also look at in the EON Tuner tab. Again, feel free to ask questions along the way. I know this is a lot of information to take in. And moving on to the transfer learning, the transfer learning block is the same thing as what I was talking about in the slides as few shot keyword spotting. So this is when we can basically do the same thing that we would do for images, which is taking our massive ImageNet model and transforming it onto our new small image data set. Basically doing the same thing for audio now. So I'm just going to leave it as default. So we have MobileNet DV1 in here, 30 training cycles, and we're just going to click start training and see what that gives us. Oh, looks like this has a DSP block. Oh, I'll type, let's say MFE. Oh, okay. So it looks like it requires a different type of DSP block, which we can easily change by going to the Impulse Design page and adding an MFE block. And then we're going to unclick MFCC and click MFE. Save Impulse. Then we just need to extract our features via the MFE algorithm. Click Save Parameters, and then click Generate Features. And so what we're doing now is we're just extracting features of our training data set based on a different algorithm for audio data, not MFCC, but rather MFE. Just a couple more minutes here. It's almost done. This will output the feature explorer that we've seen similarly in the MFCC page. And then we should be able to do few shot keyword spotting. Great. So we can see that we even have another pretty wild looking separation. And the feature explorer uses this algorithm called the UMAP algorithm. We have documentation about this in the FAQ section of our documentation. There we go. So as you can see, audio data is not just three-dimensional. It has many different axes with a bunch of different data. So we use an algorithm called a dimensionality reduction algorithm to map these features that we've extracted with the digital signal processing block onto a 3D visualization, which is pretty cool. So I recommend checking that out in our documentation. So that's the MFE block. And then we're going to move on to, yes. So, so someone had the question where we just encountered that on we just encountered this issue on the same thing for transfer learning for keyword spotting. The error basically says this block requires a DSP block of type MFE, not MFCC. And what we just did to fix that was we went to the impulse design page, and you just scroll down to click on add a processing block. And then next to MFE, click add, and just follow the same steps that we were doing for the MFCC block, which is click on MFE, click on save parameters, then you can generate your features, and then you should be able to do the transfer learning. And make sure on the impulse design page that you have your input features as MFE rather than MFCC. And then just click save impulse. Hope that answers your question. Feel free to also ask in the chat. Transfer learning. So we should be able to be good to go. I'm just going to leave everything default and see how that goes. And great. So now we're taking the extracted features from the MFE block and passing them through the transfer learning model that we have selected on our impulse design page. And this is just going to take a few minutes. So yeah, so the check on the impulse design page will be under the input features on the purple section. Make sure you uncheck MFCC, or make sure there's no arrow next to MFCC, and you select the arrow next to MFE. So you're using the right input features from the right DSP model into the transfer learning block. Just a few more minutes and we'll wait for this to be done. So now saving the best performing model, we've passed all of our extracted features from the MFE block through the MobileNet V1 architecture layer that we have here and the transfer learning or few shot keyword spotting block. And now it's saving the TensorFlow Lite model, and it will output our performance results. And I'm interested to see if this actually will perform better or have a better percentage accuracy compared to the classical keyword spotting model. It may or may not. I think we might be able to get a higher accuracy if we did more training cycles and had a different learning rate, but we'd have to see. We'll just have to see. Sorry, y'all, it's just taking a few more minutes. Okay, great. Oh, so interestingly enough, few shot or transfer learning keyword spotting in this case actually performed worse than our classical keyword spotting model. And that could be from a few different things. That could be because of the number of training cycles that we have on our neural network classifier classical block compared to our few shot keyword spotting block. It could also be because of the learning rate that we have selected, which is a bigger learning rate. If we lower that to be 0.05, we might get higher accuracy, depending on various things. We can also change our validation set size. We can also turn off auto balance data set. These things might all change the accuracy of the model, but this is actually interesting. Would need to look into why this is happening, but it's not too far off from the classical machine learning, classical neural network classifier here as well. But you get the same output or very similar looking output from the classical transfer or classical neural network classifier block. It's a mouthful. But you can see of all the samples that you've uploaded into the project, which were mispredicted based on the model that we just trained with the few shot algorithm. And you can see exactly where that sample came from and what it sounds like. And you can also change the number of training cycles and retrain to see this updated training performance here as well. And you also get the same sort of on-device performance output, the inferencing time, the peak RAM usage, and the amount of flash usage. I think this might be increased now that we have added another DSP. Yeah. So we could also go back and delete some things, and that would change our latency calculations. What's happening here? The latency calculations have increased because we have added more code. So what this essentially implies is that we'll have 2 trained models and 2 DSP codes on our device when we deploy. But in reality, we'll only have the MFCC, for example, in the neural network. So we're just going to go back and ahead and delete those and go back to the classical version, which is what I sent you guys in the public version that you can clone to your own project. And we'll keep discussing that version. But you can easily see few shot keyword spotting and transfer learning from studio.edgeimpulse.com/evaluate again, which we did a little while ago. So great. So we have a really good performing model for our application for our Hello World keyword spotting model, and specifically for our use case. Obviously, if I was doing fall detection for humans, like in an old folks home, I would want this accuracy to be closer to 100%, which is where the application testing tab is going to come in really handy. But today, our accuracy is 94%, which is great for just determining when my phone is hearing Hello World. Moving on to the EON Tuner tab, we also talked about this a little bit earlier, but I just wanted to do it from scratch to show you what this looks like. So the EON Tuner page on a fresh project will show you nothing. What you'll need to go ahead and do is click on Configure Target. And then today, because we're doing keyword spotting, we're going to do selecting on this type of data set category. But we also have data set categories to optimize for various other types of use cases, such as audible events, like breaking glass, or continuous audio applications like water running or alarms running, things like that. But we're going to select keyword spotting. And we're also going to select our target device, which is a Cortex M4F. We can, again, select a target device of any other type of hardware that we have officially supported in Edge Impulse. If you're using a device that is not officially supported in Edge Impulse, that's no problem. Just select the device that is most similar to the one that you're going to be using in the real world. Looks like we have a question. What happens to a sample uploaded today that is not labeled? If you're using the tools that we have used for the evaluation tool or for the crowdsourcing blog that I put in the chat somewhere, you will not usually have unlabeled data. But if you do have data that is not labeled and you were able to upload it into the studio, you'll just go into the data acquisition tab, click on the label, click on the sample, click on the 3 buttons to the right, and then just click edit label. If there's a sample that you've uploaded into the data acquisition tab that has no label, I'm honestly not sure what the studio does. It might not just use it in training, or it might have an error that says you have samples that are unlabeled. Oh, interesting. I guess we can just try out this theory right now. So I've removed the label from a couple samples. Oh, interesting. Now I'm curious. Let's see. Okay, so we've removed the labels from these 2 samples. And now we're going to go into MFCC. I think I might give it. Okay, I see. This is actually good. I've never seen this before. I might write a bug report for this. But basically what has happened is it's interpreted the blank label as a label itself. So you can see here this little parentheses. It's shown you have 4 classes now: blank, hello world, noise, and unknown. So thank you. That's awesome. You just helped us find a little bug. But this actually might still fail on us because the Python scripts might not know what blank is. So we'll just have to see. I'm very curious now. Looks like it's not failing. I wonder if it will output 4 classes over here. Jorgen, I'm sure I'm mispronouncing your name, but if you want to add to the Q&A or to the chat, what would you expect to happen if there were samples uploaded that had no label? Would you expect them to be ignored, or would you expect the studio to prompt you to label them?
Jenny, I would just like to mention that you can actually unmute people's microphones if you want to speak to anyone directly, if that makes more sense.
Oh,
or maybe you
I've honestly never done that before.
Maybe
so I don't know
how. Let me just check. It's in. Oh, maybe it's just me, but I can also make you the admin person. Make host.
Oh, interesting.
And then in the attendees, you can allow to talk, just in case there's a more complex question or something.
Okay, well, I've allowed him to talk. If you would like to, answer that question, or we can just do it via the chat. But it looks like it did ignore the MFCC generate features tab did ignore those 2 samples that we removed the labels from, even though it looks kind of weird here. I'll run a bug report for that. That's interesting, but it looks like nothing really happened and it just removed those 2 samples from the resulting feature extraction set. But interesting. I love learning new things every day. Thank you so much. So we'll go back to the data acquisition tab and add labels onto that again. And I will write a bug report for that. But it looks like nothing happens. So it shouldn't affect the resulting model at all. You'll just not be including those samples, it seems. You'd expect it to pop up to say, you'd expect a pop-up that says label your unlabeled. For sure, for sure. I'm wondering also, we also have this ability to enable and disable samples. So I wonder if we could just have an ability in the studio that says, hey, looks like these samples are unlabeled. Do you want us to disable them in the meantime? Because I could also see a use case where you could have like maybe hundreds of samples that are not labeled yet, but you also have hundreds that are labeled, and maybe you just didn't want to use those for now. So you could just have a prompt that says, do you want to disable the unlabeled samples? So it's something to think about. Feel free to chat about that in the chat if you have any ideas. We're very agile, so all these suggestions, all these changes, you might even see them in the studio like tomorrow. So let me know. Okay, so I've re-enabled these samples, and I'm going to go back into the MFCC block and generate these features. We don't have to do this again. We can just wait for it in the background. But I wanted to mention a few more tabs. Wanted to mention a few more tabs. Sorry, I was looking at the questions. So we've looked at the EON Tuner tab. Actually don't know if we finished that. I think I got distracted by a question. So we're going to select keyword spotting, Cortex M for F, and time for an inference. We're going to do 100 milliseconds and click save. We'll see how that goes. Because I think the other EON Tuner example, we did 1,000 milliseconds. We'll just have to see. Okay, so I've set my target optimizations, which is for, we're going to be trying to create a bunch of different options via the EON Tuner of various neural network architectures, various DSP configurations in order to optimize for the device that we've chosen and for the use case that we've chosen for our data set. So all I have to do is click Start EON Tuner. And it looks like it's not doing anything, but if you want to see the console output, just click on this little button in the top right corner right here, and you can see the job output. This will take a while. This may take quite a long while, depending on the project that you have. But you can already see it start to output a bunch of different combinations of things. And I think you'll also get an email when the EON Tuner is completed. But you can see an example of what this looks like done. Over, where is it? I think I closed it. And now it's gone. Anyways, we saw it earlier. And we can also sort of picture what it looks like right now. Great. So this might take a while because basically what it's doing is it's doing the feature extraction, DSP page, and the neural network classifier. It's doing all of those at the same time in parallel right now. It's basically spun off a bunch of jobs in our cloud web server, and it will spit those results back when it's done all at the same time. But it may take a while depending on the architecture layer configuration that it's chosen, the DSP block that it's chosen, and other things. So we'll come back to that in a moment. But the next thing I wanted to touch on was the live classification tab. Oh, I guess we need to train our model. So we need to go back. Just a few more minutes. Okay, we're just gonna wait a couple minutes here. Or I guess we could find, okay, just gonna go back and selecting sorry, right now what I'm doing is I'm finding a trained project that we've already completed so I can go back. Okay, great. As you can see, I've opened up a Harvard University project, and this is basically what I've done to create our project today. I did a workshop with them a little while back, so I'm just using the same data from that day. And so this is exactly the same project, but in a different configuration. But I just wanted to show the live classification tab. You can very easily test. Yeah, Ayush, what would you like to know about the EON Tuner? So basically, the long story short of the EON Tuner is that there's not one right way to do your neural network architecture configuration. There's a ton of different combinations of things that you can do, a ton of different neurons, a ton of different layers, a ton of different combinations of DSP blocks in order to get a completely functioning working model for your use case. So the EON Tuner basically does is it goes through all of those thousands combinations and sort of decides and helps you figure out what would be the best one to get the highest performing accuracy. And this will also output the various latency calculations for every single combination of things as well. So this takes quite a long time because we're trying to get every single combination of every single neural network configuration and DSP block combo. So this will take a little while to run, but I think I had, where is it? I did have one that we can look at. So this is an EON Tuner page that has completed. And as you can see here, the performance latency calculations for the time for inference and the DSP memory size and the neural network memory size, this is the RAM and the ROM, will change depending on the combination of various things. And you can see the performance accuracy changes depending on the combinations of things as well. So it's really, really interesting. You can have a really highly accurate model that has very low DSP and neural network memory usage or very high, and you still get the same accuracy. So it's a really easy way to compare, the trade-off of things that you can choose within the Edge Impulse Studio. And if you want a more detailed explanation of this, we have documentation on it on our website as well, and I'll post that in our chat. And we have, if you do a search on our YouTube page, we have a bunch of, our CTO, Jan, has also done a few talks. And my other colleague, Matthias, has also done a few talks only about the EON Tuner. So I recommend checking those out as well. And I'll find those links to that after this workshop and send them to Shelly, and she can send them out. Where is that EON Tuner documentation? Here it is. So I recommend checking that out as well. Okay, where was I going? Okay, so our Hello World keywords body model has retrained itself and finished again. But I wanted to check out the live classification. So throughout all of this, what are we, 2 hours and 5 minutes into the workshop? We still haven't deployed our model onto our device. And honestly, I'm going to say that's the easiest part of tiny machine learning. This is the hardest part, but as we've seen, it's really not even that hard because I have not written any code. So now that we finally trained our model, we can make this even easier by still not deploying to our device. We can directly test how well our model will perform on real life data by uploading brand new test samples directly from the web browser as well. So I can just go to the live classification tab and I can classify all of my test samples individually from this tab, or I can also upload brand new data from the device that I have connected to my project. I can reconnect my phone and upload new data that way, or I can click existing test samples that I've uploaded here. So I'm just going to click an existing test sample. This is a 1 second sample of the word hello world. I'm going to click load sample, and this will just basically take the extracted features from the DSP block on this new unknown sample that the model has never seen. It'll extract those features and pass those extracted features into the model that we've just trained. So we're not doing any more training right now. We're not doing any more model information. We're just passing a test sample that the model's never seen before into the trained model and seeing what the model predicts it to be. And it looks like this model needs some help because it says that this sample, which is supposed to be hello world, is expected to be noise. So it looks like this model needs to be a little bit better. It needs some more samples in order to increase the accuracy. And we can also select another sample here and see what that performs as. Okay, so this one was correctly identified as hello world. And you can see where the sample lies directly within the Feature Explorer cluster as well, which is really useful because on that last sample, it was mispredicted to be noise, but we can see that kind of makes sense because it's sort of not in near any other cluster of the hello world samples. So this, we either need to figure out if this was even actually a hello world sample, maybe it was mislabeled, or we need to upload more samples that are similar to this sound in order to increase the accuracy of our model.
Hello world.
And it is actually hello world. So in this case, we just need to upload more data in order to increase the accuracy of our model. But this is a really, really easy way to see if our test samples or training samples were mislabeled. Because you can have a really, really accurate model, but if your samples are mislabeled, i.e. An unknown sample was labeled as hello world, your resulting model is going to perform badly, even if it says 90% accuracy in the studio. So this is really important to listen to these samples and hear if they're actually what they say they are, which is interesting. So this is the live classification tab, where you can do sample by sample classification directly in your web browser, passing these test samples that your model has never seen before into the trained model and getting those predictions. You can also go to the model testing tab and bulk classify all of your test samples into your trained model to get an accuracy result very quickly and easily. So this Feature Explorer does look a little bit different than our other previous Feature Explorer. This is because we're only looking at the test samples now. We're not looking at the training data set. We're only looking at the test data set. So your Feature Explorer will look different, and thus the clustering will not be as distinct, because when you have an 80%, 20% training testing data set split, the test data set size is inherently much smaller. So you're not going to get as clear of separation. Again, you can see which samples were correctly and incorrectly identified to be what they were supposed to be. And you can see if there's any samples that were mislabeled. And this is the model testing tab. And again, soon under this tab, we'll have a application testing tab where you'll be able to go through and augment your test samples onto a long stream of 24 hours of data and see the FAR and FRR results. So stay tuned for that. And then the versioning tab, like I mentioned, this is how you can iterate on the accuracy and development of your machine learning project. So say I really like this model. I like how it's performing. I only have one keyword in this model, hello world. Say I want to add another keyword, which is like goodbye, everyone, something like that. I want to add another keyword, but I don't want to lose all the progress that I made on this model. So I can just go to the versioning tab and I can click on the store your current project version. And this will take all the data, all the configuration, all the intermediate model results and final models, everything that you would get from TensorFlow, wrap that up in like a zip file basically, and save it in your account. And then you can go back to this version of this project at any point in time from this tab by simply clicking on the three dots here and clicking on restore. And then, as I mentioned earlier, you can also do versioning per DSP block and per neural network block as well. So say I want to fiddle around with the parameters on the MFCC block here, but I like how this one's performing. So I can just go up here and click clone as a new version and do whatever I want. And I can always go back to the old version as well. So nothing in EdgeImpulse is a black box. Everything is very highly configurable and easily iteratable upon from various projects. So I recommend checking that out. Okay, and then finally, the deployment tab, the thing we've been waiting for. this is when we'll talk about, you've done your model training, you've uploaded your data into your Edge Impulse project, you validated that it's going to work as you want it would, as you would like it to on real world data. How do I get this thing onto my device? Well, we have a bunch of different library options here. The most common one that we see people using is the C++ library deployment option. So the C++ library deployment option is a portable C++ library with no external dependencies. It includes all the DSP code, all the neural network code, everything that you'll need to use in order to get your model built into your project as you would with any other embedded project. So it's a bit interesting, but all of the documentation for the C++ library is also available on our documentation, and I'll send a link to that right now. Under tutorials, deploy as a C++ library. So this documentation page explains exactly what is happening when you deploy as a C++ library and the types of uses that you'd want to do with the C++ library. Today, because we don't have any physical hardware devices, we are going to be scrolling down and clicking on not build firmware, but run your impulse directly, and we're going to click mobile phone. But briefly, I just wanted to talk about build firmware. If you have one of these supported devices like the RP2040, the Arduino Nano, or any device that we have officially supported that has a microphone on it, you'll see a pre-built firmware option available for you on the deployment tab. And this page will change depending on the sensor data that you have uploaded into your Edge Impulse project. But say I want to deploy my model to the Arduino Nano 33BLE Sense because that board has a microphone on it. I'm going to click on the picture for that board under build firmware. And this includes all the information of how big my model will be on my device, how big the RAM and flash usage is, and the latency. And I can choose between the int8 version and the float32 version. And this will create a pre-built binary that I can directly drag and drop onto my board via serial connection. So this is a really easy way to rapidly create prototype applications for your board that you have that is officially supported by Edge Impulse. If you don't have an officially supported board, it's still quite easy to deploy to your device. You just need to integrate the C++ library, the Arduino library, the Simsys pack, etc. And we have instructions for deploying on all of these various boards in our documentation under running your impulse locally. And there's also guided videos for every single platform as well, including, like you mentioned, the RP2040. Where is it? Here it is. I added those in the chat. Okay. So, but today, because we don't have any hardware, we can still run our trained model on the edge. We don't need hardware for this because it's a keyword spotting project and our phone has a microphone on it. So we're going to scroll down to the bottom and click on run your impulse directly. Either you can do your computer or your mobile phone. Today I'm going to do the computer so you guys can see what I'm doing. But if you're at home, you can always click mobile phone and you can follow the step-by-step instructions after you click on build. So this is essentially what will also happen on the mobile phone. What is happening is my web browser has said, hey, get the project that I've trained from Edge Impulse, build it in with the WebAssembly library that I've deployed from my project directly in the web browser. And then we can do our keyword spotting directly on the edge. And I just want to be very clear, what is happening is I'm using the deployed WebAssembly library from the Edge Impulse project within my Google Chrome web browser. So it's not connected to the internet. It's just using a downloaded library that I have from Edge Impulse on the edge. So what I'm about to do is keyword spotting without any connection to the internet. Hello world. Hello world. Hello world. And so without any connection to the internet and without having to write any code, I can do machine learning on the edge directly on my computer or on my mobile phone. And if you guys want to try this out on your phones, you can go ahead and go to docs.edgeimpulse.com/workshops and scan this QR code. And this will do exactly what I just did on the computer, downloading that trained model and running it in your web browser on the edge. And when I say on the edge, I just mean without any internet connection. Of course, it does need internet connection in order to download the model initially, but when you're doing actual consumer professional development, the model will be in memory on the device already. So you can scan this QR code here to do the exact same thing and prove it to yourself and on your own phone that the Hello Keywords Body model works on the edge. Fail to load, fail to build binary. That might be because I changed the project. So hold on, let me try. Oh, you're right. Fail to load. I think this is because I changed the project. So let me very quickly create a new. Let me create a new QR code. Okay. Okay, okay, so I think I have the QR code up, one that should work. So go ahead and scan this one that I have up on my screen on your phone, and that should work. I think I just have an outdated QR code on the workshops page, which I'll update right now. Copy image. Edit. We're live fixing things. Delete, paste. Okay. Merge. So if you refresh the workshops page, this should be the correct QR code now. Yeah, it should work. Great. Yay. Live debugging. I love it. Okay. So great. Let me know if the keywords body model works for you. This one may or may not, depending on your accent and whether we have a uploaded sample set related sort of sounding similar to your voice. Because like I mentioned, the keywords body model that we just went through is the classical version of keywords body, not few shot. But yeah. You'll of course get better results with the few shot from studio.com/evaluate. So yeah, all these instructions for the Hello World keywords body model are available here. And I guess we have like 23 minutes left, or I guess we have 40 minutes left, but if there's enough people that are willing to participate in this, I thought we could create a crowdsourced model in Edge Impulse altogether. So we can make a model specifically for everyone who's watching today.
Excellent. Let's try that.
Yeah. Let's see. Okay. Let me find it. I'm going to take a 2-minute talking break. Okay. Let's see. Okay. Let me make sure this QR code works now.
Can I help even though I haven't made an account yet?
No, I think it's all good. Yeah, so everyone here, even if you've not made an Edge Impulse account, you can contribute data right now. So what we're going to do is I have created a custom project for us. Where is it? Let me find it. I've closed too many tabs. One moment. Okay, so everyone who is paying attention, yay, Ayush, I'm so happy to hear that. I'm glad it's working for you. I figured we would make a new model specifically based on our voices during this final time that we have left of the workshop. Thank you guys again for being here and doing this with me today. But yeah, so just go to that link that I posted in the chat. And what we're going to do is we're going to scan this QR code from the cameras on our phone. And this is going to essentially open up a keyword collector application. Very similar to the other applications that we've done to classify on our device, and very similar to the studio.edgeimpulse.com/evaluate in terms of collecting data. But now we're all going to collect recordings of our voice and upload it to the same project instead of each individual project. So I figured today we could do the keyword play music. And this could be the start of a model where we want to deploy to a headset, where we could say stop music, play music, next song, something like that. But the very first keyword that we're all going to collect is play music. So go to that workshop page that I put in the chat, scan that QR code, and you can also follow the instructions on this workshop page here. But you're basically going to say play music into the microphone on your phone, and then we will see how all those get uploaded to our project. So I'm going to mute my microphone right now and upload some more samples, but please go ahead and follow the instructions on this page and upload recordings of your voice saying play music to our crowdsourced project. So I'm going to mute and do that on my own.
I've done mine. I have two colleagues here. Should I ask them to do it as well?
Yes, that'd be great. Okay, I'll give us like a minute or two, and we'll basically just retrain this model based on all of our new voices. But I used to ask the question in the chat, how can I do this on my own? So I posted that blog link in the chat, so feel free to check that out. But this is also, this keyword collector application is freely available for everyone as well. So you can do this with your family and do your own keyword spotting that way to make your own automation system based on your own language in your own home. Great. Thank you guys for uploading all that data. Really, it's really always gives me the fuzzies when I see all the samples coming in. But let's take a listen here. So everyone uploaded to the training and test data sets. And with the keyword collector tool, it automatically splits all the samples that we just recorded on our phones into the training and testing data sets. So we don't need to rebalance because we still have that 80-20 split. So it makes it really easy. So let's just take a listen.
Play music.
Great. So now we have 20 minutes of unknown play music and noise. And what we can do now is just do the exact same thing that we did on the previous Hello World keyword spotting, and do that way. So let's actually do few shot this time. We're going to do the MFE block and transfer learning. And I think this is good. I think we're going to set it that way. All right. Save impulse. We're going to set everything default and see what our accuracy looks like. MFE, save parameters, generate features. Then we just need a few minutes. But yeah, please check out that blog on utilizing the power of the crowd. Actually, let me, too many windows, too many tabs. Okay. Yeah, feel free to check out this blog. This is all the instructions you need in order to create the exact information that I have in the workshop page on a different window that I cannot find right now. But anyways, yeah, all those instructions are there. It's relatively simple. You just need to know how to create a QR code, but it's easily generatable from this website. So I recommend doing that. Okay, we're going back and we're training our MFE block. Okay, looks like it's almost done. Oh, cool. That's a pretty cool, yeah, I like that. It's a pretty cool, it looks like a sword. Anyways, so we have a really good separation between our unknown noise and play music classes. And of course, we have a pretty small amount of play music data, but this should be perfectly fine for our few shot algorithm. Hopefully, we'll see how it goes. So now that we've extracted our features, we're going to pass these extracted features into our transfer learning algorithm. I'm actually going to just increase the number of training cycles here to 40. Let me do 50, and then decrease our learning rate to 0.05. I just want to see what that does. I'm honestly not sure. On our previous transfer learning, it was 30 and 0.01, so I thought we'd do something different this time. And this might take a little bit longer because we've increased the number of training cycles. Where did I put that workshop page? Okay. And then I'm just going to paste this link in the chat. This is the next workshop page that we'll be following along with. Some of these links don't work yet because I need to make the project public. But you can go ahead and click on that link. And this is where we will then, you can clone the custom project that we just created into your own account so you can have it for the future. And other instructions here as well. So you can create the same sort of model in the future on your own time as well. So just a few more minutes while our model is training. Looks like the accuracy is looking pretty nice. So we'll see how it goes. And then we'll be able to deploy this model onto our own devices and see if it works in the real world using the few shot algorithm or the few shot transfer learning neural network architecture. Just a few more minutes. Oh, actually, I put it in the wrong chat. 1 second. Up. This is the next link. So now we're saving the best performing model, and we'll get the performance output in just a moment. Just a couple more minutes. Getting closer. Well, if you can imagine, this is actually going pretty fast, but if you were to do this training on your own computer, it would take forever. But the perks of using Edge Impulse is all of this training and all of the resources that are needed to use to build out these models is done in our cloud, on our cloud servers. So that's another great advantage of using Edge Impulse over doing TensorFlow on your own computer. But great, so we have our model now output. Looks like we have about 90%, 89.6% accuracy, which is pretty good on the amount of data that we have uploaded, which is not a lot for Play Music. So as I mentioned before, you can see all the incorrect and correctly predicted training data set samples on our validation set. You can see what everything was supposed to be predicted as, but it was actually predicted as unknown or noise and other things. So all of those are available here. And now we're just going to do our model testing tab and classify based on all the samples that we have uploaded just recently and see what our real life performance looks like, or our close enough to real life performance looks like. Just a couple minutes and we'll see our model testing results. Hoping it's a similar for accuracy percentage to our transforming block. Great, and it is. Very pleased. So we have an 89% accuracy based on the test samples that we've uploaded to our testing data set. And now what we can do is we can all deploy our brand new crowdsourced Play Music keywords body model onto our phones. So I'm just going to go to the deployment tab, scroll down, click on mobile phone, click on build, and then we can all scan this QR code on our phones. And then we should be able to do few shot keyword spotting with the keyword Play Music directly on the edge on our mobile browsers on our phones. Oh, fail to build binary. Interesting. Okay. If you get failed to build binary, I would just refresh the web browser. It might be because we're all scanning this QR code at the same time. So we might need to just stagger the job building. but yeah, just try refreshing your web browser on this page, and then it should work. Play music. We'll try it on, let me find,
It works for me.
yay, great. Does it recognize your,
Yeah,
great.
it does. But it failed the first time, but then when I refreshed, it worked. So
Great. It might just because we all scanned the QR code at the exact same time. But what I'm going to do now is I'm going to version this so you guys have access to it in the future from the link in the workshop page. Yeah. Great. So I know this is it's kind of underwhelming, but it's pretty miraculous how quickly you can get from noise and unknown, just sampling a few of your coworkers or colleagues or family and friends' voices and getting a very quick, very accurate keywords body model working on the edge without any hardware and without having to write any code. So I recommend trying this with your family and your friends. And if you have embedded hardware, go ahead and follow documentation on our website and deploy it onto an embedded device or something similar to a headset. And you're almost to production quality. Great. I'm so glad to hear it's working for everybody. That's awesome. I'm just going to wait for this to be done versioning, and then I'll send you guys the link so you can clone what we made today and iterate upon it on your own time. You can add some more keywords and retrain the model and see how it works. And you could even use it. You could even potentially use it to control your computer. You can make your own stop music, play music, keywords body model that you can use to control your computer, for example. There's sort of endless opportunities here for what you can do with tiny machine learning and audio applications. So here is the link to our crowdsourced project.
do you mean that's what, I mean, that would just work on a product
Yeah. So
without opening? Okay.
So you could just take this model that we built today and integrate it into a consumer audio headset that has a microcontroller. So here, if you can see my picture, this is a microcontroller. Say it was embedded in a headset that I had, I could deploy this model onto the microcontroller and be in production today with this model that we just built.
It's really impressive.
Yeah.
Yeah.
So the steps from here, everything that we did today is like no code, low code. But in order to get things into production, you will need some sort of embedded engineer to help you do that. But embedded engineers will know how to use the C++ library output that I described, and also that's available in the documentation as well. But if you're not an embedded engineer, I also recommend giving it a try because honestly, it's not super hard, especially if you have any familiarity with Arduino, because you can do Arduino library as well, which is also super simple. I recommend giving it a go. But here's that information as well. So yeah, I also wanted to mention the library output from the deployment tab is also freely available. You could take the output from this model that we created and put it onto your commercial professional headset today for free. We don't have any royalties on these libraries. Basically how Edge Impulse works is in order to make money, we have organizations like Polycom, Sony, these companies pay for enterprise subscription. So the cost of using Edge Impulse to create these models and deploy to your edge devices is not based on per device. It's based on subscription per month. So if you're interested in that, please email us at hello@edgeimpulse.com and we can set you up with a professional demo with our sales team.
That was my next question. How do you, what is the business model here?
Yeah, and obviously, I'm not on the sales team, so the sales team will have a lot more information about how we actually make money. But that's essentially it. It's not per device, it's per subscription of the platform itself.
Okay. Wonderful. It all seems very straightforward and
Yeah.
easy to get started with.
I think there's a couple more questions. Wait, can we add? So your question was, can we add 2 words in the keyword spotting model, like play music and music play? In this case, we're in that weird time where I think play music and music play, those would be 2 distinct keywords. So you would need to upload classes and upload samples for each of those 2 distinct keywords. So play music is one keyword itself, and then music play is another keyword in itself. But so my example was, you can add a bunch of samples, like 20 or so samples for play music, and then you can add 20 more samples for stop music. And that would be 2 keywords within your keyword spotting model. So I recommend giving that a go at home and trying it out. Just follow the instructions as we did today in this workshop. It's very simple, just top to bottom in the studio, and then deploy to your phone and see if it works. And I think that was all the questions.
I think you're right. Wow, great. Is that the end of the workshop for today?
Yeah, that's pretty much it. I guess we could answer some more questions if anyone had any. But yeah, I hope that was interesting to
Super
everyone.
interesting. And we also had, in the time, like since the event started, I had 2 emails about making other workshops.
Oh, great.
So people are really interested, and
Yeah.
to learn more.
Great. I'm excited to hear that. And happy to discuss with anyone in the audience or anyone who watches the recording. Happy to discuss more over email or on our forum at forum.edgeimbles.com.
Oh, maybe can you give us that link as well? And I'll add
It's
it.
posted very high up in the chat, but yes, I will post it.
Okay, maybe I have it already then. That's great.
And then here is our email. And then my personal email is this, and I will just put it in the chat.
Wunderbar. Excellent. Okay, I think we have all of your links.
And I'll just stop.
Nice collection.
Anyways, that's pretty much it for my webinar. If anybody had any last minute questions, but thank you everyone for coming. This was really fun. And the 3 hours went by very quick.
Yeah, it really did. Thank you so much, Jenny.
Yeah.
You're a real pro, and it was really clear and concise and easy to listen to you. And yeah, I think everyone enjoyed that. There were like 70 people signed up. So, but some were in China, some in the US. So I guess, yeah, they weren't out of bed yet.
Yeah, I'm sure. Yeah, it's like, it would be like 3 or 4 a.m. in the United States, and it's just an awkward time. But they'll watch the recording, I'm sure.
Yeah, so we're going to send it out to everyone, and of course share your contact information as well.
Great.
And I hope we can do a real life event next time as well. And maybe we discussed having a focus on medical devices. So yeah, a little bit more focused on the hearing aid industry and what they could use this platform for. So
great. Looking forward to it.
Yeah. Thanks everyone. And we're going to send a questionnaire as well afterwards. So if you could spend a couple of minutes to fill it out, that'd be really helpful for us to get some feedback. And yeah, keep an eye on our newsletter and events, and see you for the next for the next one.
Thank you so much.
Thank you, Jenny. Bye.
Bye.